Okay, I need to clarify the marks for the project, right? So the mark you got, right, was for the practical part of the project. I will now go through every single hand in. I assume the correctness and the comments and the style and everything was checked. And then I throw an eye over what I think of your practical results versus your reports. Because frankly, some of the reports were just junk. Okay? Not nice. I'll put for the next project, I will put the later of the document on the web so that you can actually make a nice looking LaTeX document. Okay, if you don't know how to use LaTeX, then find out. It's easy. And it produces wonderful looking documents, right? So your mark that you got on the mark sheet is not your final mark. It's your final mark as far as the coding style and the comments and the results and so on are concerned, right? Otherwise, my distribution of marks through the class, if I type in the marks currently, do this around about 90%. So a lot of you took an immense amount of trouble with the reports. Thank you very much. That will increase your marks for the project. Some of you really, really took no trouble at all with the reports. That's not nice. Okay. So your final mark will be handed out by next week. I have a horrible week ahead of me with conference deadlines and so on and so forth. So I'll try my best to get your final mark to you as soon as possible. Note, if you pass the practical part of the project well, then of course you pass the project. Yes? So I won't take the practical mark and then say, oh, 1 page handwritten little report 0, now you fail. No, that is not the point. The point is giving credit where credit is due as far as the project is concerned. Okay? Is that cool? Okay. Right. For the second project, start looking at it. You have a longer time to do it for the simple reason that it's more tricky. I mean, sorting is, I call the algorithm, I get the result. I call the algorithm, I get the result. I fill it in on the report. But you have to know how to sort. It's one of those things that you have to know how to do. Many of the algorithms throughout the rest of the book depend on sorting, so I can't do sorting later. But sorting is not exciting, right? So the second project I like to think is a bit more exciting. It's a real world problem. If you do it, monkey see, monkey do, brute force, you will not get good results. Okay. I have to double check the specs still. So the specs is not, no. The report and the marking scheme, the report template and the marking scheme, I have to double check still. Because the marking scheme only talk about arrays and linked lists, if I remember correctly. My cut and paste failed me. So it's not final, okay? The idea is you shouldn't do it brute force. So the best way to handle the project is to read in the input matrix, that word puzzle, to read it into a clever data structure cleverly, and then take each word from the dictionary and see whether you find it in that cleverly constructed, efficient data structure that you constructed. Okay? Otherwise, if you just look at the word puzzle and you read it, you know, there is no clever way of doing that. So you have to do some transformation on your given word puzzle in order to successfully solve the project. If you're worried, put a question on the forum. Okay? I'll keep checking the forum as well. Don't wait until the week before the project must be in. Ludwig did this over the holidays. You know, he's an ace programmer. He's the kind of person who wins international competitions, right? And it took him a while to finish this. So don't wait until the end before you start working on it. Okay? You have 6 weeks for a reason. The reason being that I think it should take about 6 weeks to do this. Okay? Any more questions? Well, any more questions? Any questions? Okay? I will keep yelling throughout this lecture. If you can't hear me, just put up your hand, because the level of noise downstairs. Moet ek nog harder praat? Or is it a question? Huh? Yes, 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 yes. So remember that somebody picked up that the very last test, test 5, I moved to a Thursday. That clashes with operations research. And then I said the only sensible thing to do is to move the last test to the 20th of May in the exam period, right? If you have a sikte toets, if you have a repeat of one of your previous assessments, you will have both on the same day, on the 20th, which, because the test 5 is 50 minutes as usual, so you'll write your 50 minutes for test 5, and then everybody will leave, and then people who have to rewrite the previous test will continue for the next hour. Okay? Questions? Okay, so let's recap where we are after the hysterics of the demo. We are busy with searching, and we almost complete with searching, and I'm printing your tests for next Friday as we speak. Yes? I had 2 requests for Afrikaans tests. Is there anybody else who wants an Afrikaans copy as well? No? Okay, so I'll make 2. If Mr. Becker and Barnard, if anybody else wants an Afrikaans test, you bugger unless you let me know. Okay, good. Otherwise, I simply waste paper. Okay? Don't kill the trees. Okay. Where are we with searching? Let's recap very quickly. In the beginning, we had a look at something called the symbol table. And then we asked ourselves, in the symbol table, which contains key value pairs, what is the best data structure to implement my symbol table for the key value pairs? And we said, well, I can look at linked lists, or I can look at arrays, either unordered or ordered. And then we had the dilemma, if I do that, either my search is very quickly but my insert operation is very slow. Or the other way around, my insert is very quick, but my search is very slow. And the whole idea is that we find a data structure so that both insert and search are both order log n. Yes? So then we started out saying, let's make a binary search tree, a BST, which is way cool. What is the problem with the binary search tree? It is sensitive to the order of the input data. So if I input my data in a certain way, say ordered A, B, C, D, E, F, I get a worst case search complexity, which is linear. Yes, because my search tree defaults way to this, to a linked list going all the way left. So we said, well, my insert doesn't work well. So how can I rather do that? Then we looked at two, and the numbers refer to the number of outgoing links. So the number of children of a node. So a 2 node is a node with 2 children. A 3 node is a node with 4 children. And we discussed 2, 3 trees in quite some detail, but we did not give any code because there are just so many special cases happening in 2, 3 trees that it's not easy to, you can, but it's not a nice implementation. We said, let's take this idea of a 2-3 tree. Can you net die vensters bietjie maak? To get to a nice implementation, it's already when you build a Lego thing, you can just run. Kill it all. Yeah. Okay. Don't you think it's spectacular when something breaks? So that is one of the most difficult things to animate graphically. The physics involved in modeling the breakup of something is absolutely incredible. Yes, how many of you are interested in graphics? Maybe I can try a guest lecture somewhere. There's a company in Cape Town called Black Ginger. What, you know about Black Ginger? Huh? One of my ex-students are working there, and he's exactly doing this. They do movie animations. It's not my thing. Well, the movies they do is not necessarily my thing. So, but apparently there are these well-known movies that they work on. And this is one of the most difficult things. If I do the graphics, sorry, I'm off on a tangent, but it's a very interesting tangent. Imagine a wall is constructed of bricks. Now, that wall. How do I model that in graphics? Well, I have to describe the physics. The physics is knowingly intricate. If I translate this physics and then render the physics as it were, yes? And for a wall, it is fairly easy. I only have gravity and cement. When the wrecking ball hits the wall, suddenly the wall must consist of hundreds of linked elements, and each of them has a different force applied GPU just dies. Yeah. So there are ways to approximate these effects in the physical sense so that I can actually render the graphics. Wait a week. Binary search trees. If I don't know about my data structures, I can't write nice games. Okay. Binary search tree. What is the problem? It has a worst case. It's sensitive to input data. So we designed 2-3 trees, but the code is sort of yucky and there's a lot of conditions and special cases, not nice to implement. Doable, but not nice to implement. So what do we rather do? We make an map. 2-3 yes, because the code is very nice for normal binary search trees. We do that mapping for the 2-3 a binary search tree, but a binary search tree where the nodes are colored, a so-called red-black tree. And the invariant, the thing that stays constant in the red-black tree is that the red-black tree is perfectly balanced all the time on the black nodes. Yes? We make sure, and incidentally, these guys said we can invented idea of a left-leaning red-black tree, because red-black trees were known, and they showed that if you take the normal red-black tree and you make it left-leaning, I just so love that word. Left-leaning red-black tree, where the red nodes always go to the left, then it is easy to implement and you are able to, on average, get a better performance out of it. Okay, so we have the red-black tree, we map it to a normal binary search tree, but some nodes are red and some nodes are black. If that is the case, then we can use the normal methods that we implement on a binary search tree. We just have to sort of make this little check whether my link color, my node colors are still correct or not. And on Thursday morning, we covered insertion into red-black trees. Now that already becomes a bit tricky because you have to take care that your node colors are correct. If your red node insertion can cause a right-leaning red link. If that is the case, I have to do a local transformation to make it left-leaning. Insertion can cause two red nodes. What then? And there's this whole thing about when do I change the color? Yes? Okay. And there are many different special cases that you have to look at. Okay? Keeping the root black and so on and so forth. And then follows the implementation. I told you to make sure that you understand this summary, yes, and you follow the implementation. I wonder whether the red-black trees would work nicely for project number 2. Just asking. Okay. Now, in a practical application, you want to do a lot of things when you search. Remember in the beginning of the chapter when we looked at symbol tables, we said, I want to put, insert, I want to get, search, I want to be able to find a minimum, I want to be able to find a maximum. I want to be able to do a range query. Remember, we looked at in some detail at range queries while we were doing the 2-3 trees. Okay? I want to do that, and I want to do all of that efficiently. It is also possible that you have a telephone list, I don't know. Do you still, on your phone, you probably have a list of all your contacts, right? When you start typing a phone number or a name, the phone comes up with the possible candidates. So that is a range, right? So how the hell does that code work? Hopefully, yes, please, with a left-leaning red black tree. Okay, because that is the most efficient way of doing all the operations with logarithmic complexity. Yes. You have a key value pair. Oh, I see. I don't know. I sort of an example out of my thumb. Probably not quite correct. It's an interesting one, though. Think about this. Phone numbers. Sometimes I want to, what we're looking at in the symbol table for the moment is I search on a key. And so we have a key value pair. I would have phone numbers. I can search on phone numbers and find the corresponding name. What Mr. Surya now picked up is if I have this kind of situation where I want to search on two keys, you would actually have to duplicate the data structure. Might be inefficient, because if I want to search on both numbers and names, like the clever phones do, smartphones. Yeah. Anyway, so it wasn't a good example. Okay, so now today, this is going to probably be the most confusing code you will see in this course. And it is for the test next Friday. Yes, nou luister almal. It is relevant for the test of next Friday. How do I delete from this left-leaning red-black tree? Because the important thing is, if I delete from the tree, then I must maintain my invariant. What is my invariant? My invariant is that my tree stays black balanced. Okay? So you cannot somewhere go and delete. It's easy to delete, but I must delete in a way that will definitely maintain the balance. Okay. So the deletion is so intricate that we actually reconsider insertions first. So we're going to look at a different way of insertions. The difference with the insertions here. Wait, first the insertions, and once we get that, then you can start deleting. When I insert in a normal, common garden variety binary search tree, I go all the way to the bottom and I put up one node there. And we saw that that is exactly the problem with binary search trees, because that can allow this worst case degeneration into a linked list. Yeah, so the moment you insert at the bottom, you get the problem that you don't keep the balance of the tree. So we got the red-black trees where I try to insert at the bottom, but I bubble up to the root, and only at the root can the level of the tree increase by 1, the height of the tree. Yes, because I bubble up. Now this insertion that we will now look at does a top down and a bottom up in a certain sense simultaneously. So we transform, yes, on the way down into a tree, but we also there. So let's look at this.